Lesson: Cryptographic Vulnerabilities in Blockchain Systems. Cryptographic vulnerabilities in blockchain systems represent a critical area of concern for professionals focused on data privacy and security risks. Blockchain technology, by its nature, relies heavily on cryptographic algorithms to ensure data integrity, confidentiality, and authenticity. Nonetheless, these cryptographic mechanisms are not impervious to vulnerabilities, which can compromise blockchain's security promises. Understanding these vulnerabilities and implementing strategies to mitigate them is paramount for professionals aiming to secure blockchain systems effectively. The reliance on cryptographic primitives, such as hash functions, digital signatures, and encryption algorithms forms the backbone of blockchain's security architecture. However, the resilience of these cryptographic mechanisms can be undermined by several factors, including algorithmic weaknesses, poor implementation practices, and advances in computational power. For instance, the widely used SHA-256 hash function, which underpins Bitcoin's proof-of-work consensus, is currently considered secure. Still, the emergence of quantum computing poses a potential threat due to its ability to solve complex mathematical problems exponentially faster than classical computers. This threat necessitates proactive measures, such as the exploration and adoption of post-quantum cryptographic algorithms that are resistant to quantum attacks. Another significant cryptographic vulnerability arises from inadequate key management practices. Key management is a critical aspect of cryptographic security, as the compromise of private keys can lead to unauthorized access and data breaches. Blockchain systems must ensure robust key generation, storage, distribution, and revocation processes. Tools like hardware security modules and secure multi-party computation can enhance key management by providing secure environments for key operations. For example, HSMs offer tamper-resistant hardware to store and manage cryptographic keys, thereby mitigating the risk of key exposure due to software vulnerabilities or insider threats. Cryptographic vulnerabilities can also arise from flawed implementations of cryptographic protocols. Developers must adhere to best practices and industry standards when implementing cryptographic operations to avoid introducing exploitable weaknesses. The Open Web Application Security Project provides comprehensive guidelines for secure cryptographic storage, emphasizing the need for using well-vetted libraries and avoiding custom cryptographic solutions. By following these guidelines, developers can minimize the risk of introducing vulnerabilities due to improper implementation. Real-world examples underscore the critical nature of addressing cryptographic vulnerabilities in blockchain systems. The 2017 Parity Wallet bug, which resulted in the loss of over 500,000 Ether, exemplifies the consequences of inadequate cryptographic implementation. The bug stemmed from a flaw in the smart contract code, which allowed an attacker to exploit a vulnerability in the multi-signature wallet's initialization process, leading to a massive loss of funds. This case highlights the importance of thorough code audits and adherence to secure coding practices to prevent such vulnerabilities. A proactive approach to mitigating cryptographic vulnerabilities involves regular security audits and penetration testing. Security audits help identify and rectify vulnerabilities before they can be exploited, while penetration testing simulates real-world attacks to evaluate the robustness of a blockchain system's security posture. Tools like MythX and Securify provide automated security analysis of Ethereum smart contracts, enabling developers to identify and address potential vulnerabilities efficiently. These tools leverage static and dynamic analysis techniques to uncover security flaws, offering actionable insights to improve the security of blockchain applications. Furthermore, the adoption of formal verification techniques can significantly enhance the reliability and security of blockchain systems. Formal verification involves mathematically proving the correctness of a system's algorithms and protocols, ensuring they adhere to specified security properties. By employing formal verification tools like Coq or Isabelle, developers can rigorously validate the correctness of smart contracts and cryptographic protocols, reducing the likelihood of vulnerabilities due to logical errors or unforeseen edge cases. The integration of privacy-preserving cryptographic techniques, such as zero-knowledge proofs and homomorphic encryption, can further bolster blockchain security by enabling secure data sharing without revealing sensitive information. ZKPs allow one party to prove knowledge of a value without disclosing the value itself, thereby enhancing privacy and confidentiality. Projects like Zcash have successfully implemented ZKPs to provide anonymous transactions on a public blockchain, demonstrating the practical application of these techniques. Similarly, homomorphic encryption allows computations to be performed on encrypted data, preserving data privacy while enabling secure data processing. These techniques offer innovative solutions for balancing data privacy and security in blockchain systems, addressing concerns related to data exposure and confidentiality. The importance of staying informed about emerging cryptographic threats and advancements cannot be overstated. Professionals in the field must engage in continuous learning and monitoring of the cryptographic landscape to anticipate and respond to new vulnerabilities and attack vectors. Participation in industry forums, collaboration with academic researchers, and engagement with open-source communities can provide invaluable insights into the latest developments in cryptographic security. In conclusion, cryptographic vulnerabilities in blockchain systems pose significant challenges to data privacy and security. Addressing these vulnerabilities requires a multifaceted approach that encompasses robust key management practices, adherence to secure coding standards, regular security audits, and the adoption of advanced cryptographic techniques. By leveraging practical tools and frameworks such as hardware security modules, automated security analysis tools, and formal verification methods, professionals can enhance the security of blockchain systems and mitigate the risks associated with cryptographic vulnerabilities. Continued vigilance and proactive adaptation to emerging threats will be essential to maintaining the integrity and confidentiality of blockchain data in an ever-evolving technological landscape.